So now, having gone through a certain amount of formalism on atomic structure and spectra, I'm going to consider some concrete examples. And first thing is helium plus, which is really just a continuation of the hydrogen you already did yesterday. So what you have to remember is that the Rydberg formula is that the energy levels depend on the principal quantum number n squared with the Rydberg constant, and I don't know whether you did this yesterday or not, but the Rydberg constant has a slight mass dependence to it, and we'll come to that in detail in a bit when we look at radio lines. And there's a scaling with the charge of the nucleus, which of course Z equals 1 for hydrogen, so the formula is often omits that Z squared term. So for helium plus Z equals 2, so basically you get the hydrogen spectrum blown up by a factor of 4. And occasionally you see papers around claiming that hydrogen has half-integer principal quantum numbers. And in fact, someone started an energy company, which got a lot of funding, an American guy, saying that he could create energy by getting hydrogen to its n equals 1 to its n equals half state, and there was boundless energy there, which we could use. Basically, you get half-integer quantum numbers if you take a hydrogen spectrum and you have a bit of helium in there. And because of this Z squared thing, it's equivalent to making half-integer, having n equals a half. It gives you the same effect. So if you mistake a hydrogen spectrum with a little bit of helium, you can confuse yourself and think you get half-integer quantum numbers. So it's spread out by a factor of Z squared. Sorry. So basically that's all I was going to say there. You did everything else. The naming is the same. You talked about Lyman alpha, Lyman beta, Balmer, etc. They just call about helium. And this I'm a background chemist, so I'd call the ion of helium He+. But the atomic spectroscopy uses these Roman numerals. So helium neutral is helium-1, helium plus is helium-2, the alpha particle is helium-3, because you've taken off 2 electrons. So helium-1 spectra, so now we have 2 electrons, and as you probably all know, the helium is a closed shell species. It's a rare gas, or noble gas. So the ground state, because we only have a closed shell, has to be 1s0, because there's no angular momentum in there. So S equals 0, L equals 0, J equals 0. What's called the resonance line in these atoms is the first, so the longest wavelength or lowest frequency at that first allowed transition, and the resonance line in helium involved creating a 1s electron to a 2p electron, and it's quite high up. It's about 20 electron volts or 584 angstroms. That's actually off the top of most space telescopes because they tend not to go that short wavelength. So it's a far ultraviolet. It's quite difficult to see astronomically. So how many lines does this actually give you? So I've given you something there which is just in terms of configurations. But if you look at 1s2p and a little comment about configurations, you use superscripts here if you have more than 1 electron in your orbital. If you only have 1 electron, you don't normally superscript it. So this is equivalent to say 1s1, 2p1, but you don't normally write the ones. If you had 3 electrons in here, you just write 3. So this is a 2 electron problem. And if you want to think what the term you get from there, well, obviously you have S equals 2 spins, both S a half. You add a half and a half together, you get 0 or 1. And L is just given by the P. So L is 1 or P, so you get singlet P odd or triplet P odd, and they're odd because if you sum the angular momentum, you've got 0 for that, 1 to that, so the sum is 1, so that's minus 1 to the 1 is odd. So this is an allowed transition. If you go back and look at your selection rules, it obeys every single one of the selection rules. There's a strong allowed transition, and that's your resonance line I'm talking about here. But of course, you get triplet P. Now that's long-lived, that's better stable, because it doesn't give the it doesn't obey all the selection rules. It doesn't obey the delta S0 selection rule. It involves changing spin. If you take this one level further, and we consider fine structure, so singlet P, the singlet P odd, well, S is 0 here. So if you add everything, you just get J equals 1. It's your only option. 1 plus 0 is 1. But this one, triplet P, has S equals 1 and L equals 1. So that gives you J equals 0, 1, and 2. So you get 3 components. It's actually, you get that from it being a triplet. It's the same thing. This is a fine structure. The triplet is a reflection of the electron spin. You get 3 components. So again, there's only one allowed transition, which is this one, and this is still obeying the selection rules because J 0 to 1 is allowed transition. These ones are metastable. And going back to the question I got asked just before the break, actually, I'm just realizing something. This one is an intercombination line. So let's go to pen mode here. So that's an intercombination line because it has everything allowed except for delta S is not equal 0. What I realized when I was making these notes, that this is a forbidden transition because you've got delta J as 2. So that's not allowed actually by any dipole rule. So you have to go, it'll be a quadrupole line, I should imagine. And what I didn't realize, and therefore what I've written here is slightly wrong, is that is also strongly forbidden because there it has delta J equals 0, which I said was allowed. You can't have 0 to 0. And I forgot that when I was writing the notes. So actually, of these 3 fine structure components, only one of them is an intercombination line. And the other 2 will probably decay. I'm sure there are routes to decay, but reality decay even by just having a collision that converts them into the one that's allowed. Cool. Yep. So this is something called the Grotrian diagram. Grotrian was a German atomic physicist from about 100 years ago, and he came up with this structure of capturing all the data on a particular atom or ion, a single ionic state of an atom. They're pretty common. I think I still have 2 big books of them on the shelf, inherited from Mike Seaton, who was a professor of atomic physics that appointed me at UCL in the first place. And what you can see is it divides the atom according to the spin states. That's the most gross division. And it subdivides them up the top, you can see by L. So you've got L equals 0, 1, 2, 3, L equals 0, 1, 2, 3 for the singlets and triplets, in a particular case. And then this is going up in energy. By convention, these are in EV. The lines, thick lines are allowed transition, dashed lines, in this case, are intercombination lines. Sometimes they can be forbidden transitions. And the number on them, which never has any units, is a wavelength in angstroms. So they never tell you that. That's sort of understood. An important point is the ionization limit, which in this case is at just under 200,000 wave numbers. you've got any quantum chemists in the room, that's nearly 1 Hartree, just to give you a scale. And you can see that you get, because in your, I'm sure I did this already for hydrogen, because the 1 upon n squared type behavior, you get a big collision of states up the top end of this where they all jam up very near the ionization limit. And you can see that we've got the 584 resonance line here marked, that are line from the n equals 3 down to the one state at 537 angstroms. And we've got a couple of intercombination lines marked from the, there we are, this is the main one I talked about, from the triplet P n equals 2 level. You can see the splitting, the 5 structure splitting is quite significant here. Or sorry, the splitting due to L is quite significant, coming down here at 592. So that one's better stable, come from the n equals 3 as well level. So normally, you've got lots of lines within the structures as well. There's lots of long wavelength transitions between excited states as well. So these things are a way of capturing the observable lines of an atom. So they're quite useful if you just want a quick picture. You can get the Grosjean diagram up for the species you're interested in. So moving on to sodium. Sodium, as you probably know, is a closed shell with 1 electron outside it, like lithium and potassium and all the other alkali metals. So you could treat it almost as being hydrogen. So that makes it relatively simple to deal with. There's an important point about the sodium spectra, that the SPD notation that we all use comes from sodium spectra, because when these various series were originally observed, they were labeled the sharp principal diffuse fundamental, which you may notice stands for SPDF, and the lower state in each case turns out to have an S, P, D, or F. Well, I've given them as term values, they're all and level values, but actually the orbital has that characteristic as well. So those letters got adopted for them. And you get doublets and triplets, and I'll just go through why some of them are doublets and some of them are triplets, and I think that's on the rest of the slide. So SPDF, which we've talked about. I do this somewhere. No, okay, I'll go through it here. So let's look at this transition here, for instance. So you've got the doublet D has J equals 5 upon, sorry. Can't rub out on this thing, can you? Probably can. Sorry?
Is it black?
Is that? Yep, okay, that got rid of everything, that'll do. So the doublet D 5 halves has a level with J equals, sorry, doublet D has a level with J equals 5 halves and J equals 3 halves. And doublet P has a level with J equals 3 halves and J equals 1 half. And you could think that you get 4 possible transitions there. That's just combinatorics, it's not selection rules. One of those transitions is not allowed. Any offers which one's not allowed?
Rainbow.
Yeah. So this one is delta J equals 2, which doesn't happen. The other ones are all delta J equals 1 or delta J equals 0, so they're allowed. And this would be very weakly allowed by quadrupole transitions, but the reality is it will come down here way before anything else happens, so you simply don't see this. So this means you 3 lines, hence it's a triplet. In the case where you're evolving the s orbital, there's only one fine structure state. So you get a doublet because you get half to 3 halves and half to half, and they're both allowed. So these are doublets and everything else is triplets. And the sodium D lines are actually this. I don't know if that equals 3, it might be a different n, but it's yes, they're called D lines. That's nothing to do with the D here. That's because Fraunhofer labeled his big features A, B, C, D going across his spectrum. So the sodium D lines have nothing to do with any D on this picture here. And they actually come from the principal series, the P to S series.
Oh. Okay.
Thank you. We've gone too far. There we are. So that's the Grotrin diagram for sodium. And here, if we only move the outer electron, you only get doublets. If you want quartets, which you can get, you have to move an inner electron. That's much more energetic. And 2 electron transitions don't happen, basically. So we just need to worry, at least for practical purposes, with doublet transitions. So there are an awful lot of allowed transitions here. So there's only one. I think the fact that these things are a bit black and whitish is just an optical effect. I think they're all solid lines. So I think this line is meant to be the same color as this line. It's just the optics are having different slopes. This is the only forbidden transition on here, which is and it's because otherwise, well, you can decay here, so this must be quite weak. Now I put something on here, which we'll spend a few minutes on this, called the quantum defect. It's a way of representing sodium spectra as if they're hydrogen spectra. So hydrogen spectra use this very easy and simple Rydberg formula, -1 upon n squared for the energies. What you find if you have something like sodium, where you have inner shell electrons, core electrons, is that you get something which looks roughly like 1 upon n squared, but it has a small shift in it called the quantum defect. And these are the quantum defects, and I'll go through what that means. And the said Mike Seaton, who I just mentioned a few minutes ago, didn't actually invent quantum defect theory, but he was the guy who really developed it to, I would say, a very powerful scientific theory that people still use multi-channel quantum defect theory very extensively based on his work. So you apply this to any system where you only have 1 active electron. So it would work for calcium plus, for instance, because that's the same. Calcium normally has 2 electrons in its outer core, but if you had a calcium ion, then you'd have 1 active electron. And you have the normal Rydberg formula, except you replace it by an effective nuclear charge and an effective quantum number. The effective nuclear charge is quite simple. It's just the net charge held by the outer electron. So it's usually the 1 for neutral, 2 for an ion, and so forth, because it's the charge on the nucleus minus the number of electrons plus 1, because you've got the outer electron isn't counted in that n. So basically, if you're doing sodium neutral, the effective nuclear charge is 1. If you're doing calcium plus, it's 2, and so forth. So that's quite easy. What is more complicated is the effective quantum. So there's small shifts in the n value to account for this behavior, and they're normally represented by a symbol nu, and they depend in principle on n and l, where n and l are your standard shell and orbital angular momentum numbers you use for hydrogen. And the reason for representing this way, as I'll show you in a second, is that these things depend strongly on L in a very predictable fashion and very weakly on N, which means you can almost assume they're constant on N, and therefore you get a lot of information from that. So if we look at this, here we have the NL values for a bunch of levels in sodium. You can see that the quantum defect for the s orbital is actually rather big. It's more than 1 quantum number, and that's because s electrons penetrate right into the core of the nucleus. So even something with a high n equals 20 or something, will still have a little bit inside the shell of a sodium atom. So you get a big quantum defect for s electrons, a reasonably big one for p electrons, a small one for very small one for d, and basically they vanish after that. So when you have high angular momentum electrons, basically they have no quantum defect. The electrons are just outside the core of the atom. However, what you can see is that they're very constant with n. The variation with n is very small there. So they typically depend weakly on n and strongly on L, and they have this order that the low L quantum defects are bigger than the high L quantum defects, and the high L quantum defects tend to zero. And they're normally positive, they're normally a small attractive force. The positive quantum defect makes n, effective n squared, slightly smaller, it lowers the energy level. So normally the quantum defect is a slightly attractive force. And the virtue of this is that you can work out the quantum defect for, say, these three levels. You can predict this one, and then you can say what the spectral line associated with, say, n=6 is on the basis of knowing what the other quantum defects are, simply by using the Rydberg formula. For other things, you can simply develop summation progressions on the fact you know all these quantum defects. So you've got an infinite number of levels here, you can sum over things. That's multi-channel quantum defect theory quite often does that. So it's actually a very powerful way of treating one-electron systems, or effectively one-electron systems. Okay, people happy for you to move on? Just to threaten you, there's an exam question on this, so don't let me move on if you don't understand it.
So this can be applied to an IQVF relevant session.
It can apply to anything like the one electrons. So mercury, for instance, is a 2-electron isotope. So if you remove one for mercury, you have mercury and mercury plus, you could use quantum defect theory on it and it works fine. Now you'll start at quite IN. I think it's the n=8 level, which has 2 electrons in for mercury, but then you could just go up from that. So it works for anything. And it works all the way down the alkali metal series. Sodium is just the classic one, basically because sodium is convenient to take spectral, the quadrupole line, the visible, the lines line, the visible. So the original work was all done on sodium. And as I said, Fraunhofer saw it in the solar spectrum, in the visible, in the D lines. And you've probably burnt it and seen glow orange in a flame. So you've probably seen these lines with your eye. So another non-standard bit of atomic spectroscopy. And this is quite unusual because this is a spectrum which almost doesn't depend on the species you take it on. So, I mean, I didn't say it, but it was sort of implicit. The great thing about atomic and molecular spectra is that every atom and every molecule has a unique spectrum. Some people sometimes call it a fingerprint. I prefer to think of it as a barcode like you get in the supermarket because it's a set of lines and it's unique to each species, so you can identify the species. This is the one example where this is almost not true. And these are so-called radio recombination lines. What happens here is that if you have an ion, and this is particularly important, how am I doing? Okay, fine, I'm doing fine. This is particularly true in the interstellar medium where things are very diffuse, so you get very few collisions. If you have an ion, say carbon plus forms very easily in the interstellar medium. You can recombine with an electron, so you go from the electron being in the continuum to a bound state. Normally, you could do that by emitting a photon. It's a rather weak process, but if you have enough time, weak processes happen, and you form in some very high n value. So I've got these examples are n in their 30s. That's 29, 30, 37 if you can't read them. Somewhere, I think it may be on the next slide, I have a even higher example. And you get transitions through these very high n levels. And you have, unfortunately, a different notation for this, which is alarmingly similar to the notation you've already learned for the hydrogen. Well, one bit of it is the same, and it means the same thing. So you have the alpha beta notation, that's the same. So alpha is changing n by 1, beta is changing n by 2, and so forth, and gamma, etc. And the strongest lines are alpha lines. but you have n plus 1 to n are called Hn, and that's a bit unfortunate because H is also used for the Balmer series. So these are called Hn Balmer. So Hn alpha is this. N is normally a number here, so that would be here H30 alpha, whereas the Balmer series is normally just H alpha. So it's not quite the same. It's still potentially rather confusing. So you have these cascades down, and when n is very large, basically the quantum defects become irrelevant because you're so far from the central atom that you don't really feel it. And anyway, if you're an n equals 30 level, you've got up to n equals 30, the chances are you're at a very high L state, which doesn't have a quantum defect. So these things basically all obey the Rydberg formula. So if it wasn't for the fact there's a slight mass shift to do with the different mass of the nuclei, all the lines would lie on top of each other. But you get the Rydberg constant, the one we measure and you look up in the books, assumes an infinite nuclear mass. But if you have a practical nuclear mass, you have to scale the thing by the reduced mass. And this has got slightly obscured, so I'll write it up. So the Rydberg constant for an atom called A is the reduced mass with that atom divided by the electron mass times the Rydberg infinity, as I said, the one you look in the book. Quite common is something called RH, which is obviously the Rydberg constant for hydrogen. That was also normally given in the books. I don't know whether Bobby gave that value yesterday. Yep. And you also get RD as well for deuterium. So these are sort of standard ones, but in principle you get R anything for any atom you care to name. And the reduced mass in general, and we're going to meet quite a few reduced masses in this course because this becomes very important also in molecular spectroscopy, is product of two masses divided by it. You can actually write it also as 1 upon mu equals 1 upon m1 plus 1 upon m2. That formula are the same. You just get from one to the other. And it's the effective mass that the whole thing orbits. It's an orbital problem with the electron, the nucleus, not quite the centre of gravity, but very nearly the centre of gravity. It's the effective mass of that orbit. So if you have the case here, we have an electron and we have a atomic nuclear mass. Or to be absolutely strict, it's the atom plus all the other electrons. Being really strict about what the mass is, and it's given by that formula. And if you put that formula into there, you get this is actually what you need to do to see the shift in the masses. Here I've just got hydrogen, and they're done in these funny velocity units. So this is not a great picture, but this is zero velocity relative to where you'd expect that line to be on Earth. And you can see that all these components are all shifted. That's 200 kilometers per second. So I guess that's about 40 kilometers per second. So that shifted away from us, so-called blue shifted. And you can see they're all lying roughly the same shift. So they're all coming from the same region of space. That's it. That's the assumption. But if we go on, and the next slide shows an example with different atoms. Sorry, I need to do this first. There we are. Shows an example with different atoms. So this is now n equals 114, so we're getting really high. The record is certainly above 200. I think it may have even reached 300 in recent years. And you can see we're right in megahertz frequencies here. This is an electronic transition right down in the microwaves. And here we have hydrogen, helium, carbon, and they close up. So when you get beyond, I don't know, it's somewhere in beyond the next period of the periodic table, you normally can't resolve them. They'll just sit on top of each other. There's a difference in the reduced mass gets so small. So, yeah, you can see here, I've worked it out. So for hydrogen, this is a 51.51072 megahertz. 51092, 51097, and when you get to infinity, it's 51099. So the difference between this and this is really very small. They eventually all end up just on top of each other. But you can still distinguish helium and hydrogen and carbon using this method, and presumably anything lighter than carbon. The boron and beryllium and lithium are all pretty rare elements. What is that? And when I was telling you the notation, I was telling you that it's H for hydrogen, actually is the atom name here. So it's not H for everything, it's H for hydrogen, but it's C for carbon, He for helium, and so forth. So when I said it was Hn alpha, that was only for hydrogen. I should have said that at the time. So these things are called radio recombination lines. They're quite easily visible in the interstellar medium, providing you have a telescope which goes to high short wavelengths. And as I said, that's particularly ALMA in Chile. The Atacama telescope array is very good at looking at these sort of things. And I assume the SK will go to even longer down these sort of transitions. Right. So I have two pictures here, slightly different frequencies. One is a single line. One shows three lines. Anyone got any ideas what the structure might come from? There's more than one answer to this question, so I hope I'm going to get a few from you. Yep. Sorry? Yeah, so it could be, you're saying it's an atomic structure. It could be true. So not. So this could be defined structure. Any other possibilities? In a sense, it's not quite how I put it. Normally broadening just gives you a broadened shape. I think actually this is caused by the fact that this cloud this is not one cloud, it's clouds with different velocities. So I think it's actually one line, but it is, in a sense, it's a line shape. It's caused by the velocity of the object, not by the peak. At this point, I'm going to go back to sodium because I remember I told you I'd tell you about one of the methods of So you have these multiplets, which I went through. Here we are. And I said, for instance, for this transition, you get a doublet, you get So you get two possible transitions. These transitions are not the same intensity. They're actually weighted by 2J plus 1. And we'll come back, actually, that's also true for molecular spectra, where you get factors of 2J plus 1 in the intensities. So 2J plus 1 here is 2. And 2J plus 1 there is 4. So if you have a nice optically thin doublet resolved, this transition should be twice as strong as this transition. If it's optically thick, they're the same intensity. So you can use that as a very simple measure of whether you're looking at something which is optically thin or optically thick. And obviously they could be somewhere in between, in which case you get some estimate of the degree of optical thickness. So this is 2 times stronger than the other one. Okay. Right, a little bit about data sources before you'll find that this section of the course, we always end up with hydrogen because hydrogen breaks all the rules. So before we get back to that, if you want to find out about this, where do you look? I would say, and I will still say, NIST, but there's a slight caveat. Our highly esteemed President of the United States has decided that it would be a sensible thing to close the NIST Atomic Physics Group, so it doesn't exist anymore. The database is still there. Well, yes, it is still there, even though they're on furlough, because the American government is still shut down, I think.
They're right. Probably they're looking at shifting this to something.
Yeah, that's a problems here at the moment. As we speak, the American government is not shut down. So if you go to any NASA website, for instance, NASA website has a very nice catalogue of all the exoplanets that have been observed. You can't get there at the moment; it's closed because NASA is furloughed. I think NIST is furloughed as well, but they don't close the website. So the NIST website is still working, but the Atomic Physics Group doesn't work there anymore. They're moving to NASA Goddard, but NASA's budget is also under threat, so I'm not quite sure how stable that's going to be. So at the moment, this is a great place to go for your atomic data. It comes in two forms. It has a lines database and a levels database, so you can look at the levels in great detail, and then you can look at the lines, and it gives you Einstein air coefficients when known. Einstein air coefficients, I mentioned verbally, they're the transition probabilities, have units of seconds to -1. There are an awful lot of different ways of giving transition intensities. I much prefer Einstein air coefficients because the units are completely unambiguous and understandable. They're seconds to inverse time units. Nearly all the other ones have really strange units that leave your head scratching, and there are lots of them. There are whole review articles comparing different methods of giving intensities. So I'm going to stick here to A coefficients, and our database sticks to A coefficients, as does NIST. So just a warm up for what we'll be doing after lunch is we're going to start doing in molecules. And the big difference between molecules is that they have extra degrees of freedom. So basically an atom, besides the electronic motion, has 1 degree of freedom, and that's that the atom can translate in space, X, Y, and Z. So that's actually 3 degrees of freedom, should I say. A molecule has those three degrees of freedom, but they can also rotate. If it's a 3D object, rotate in 3 directions, and then they can vibrate. So we're going to have to go through all the different degrees of freedom, and then they have electronic motions, exactly like the atoms have. But in a sense, the electronic spectra of molecules are important, are the least important of the 3. Okay, so that's all you're going to get from atoms from a combined effort of me and Bobby. So if there are bits you don't understand, now is your moment to stick your hand up and say, can you just go back and talk about this or why or whatever? So I will pause there. Have I got any questions? So I remind you, you've got an exam on this on Friday. So exactly this time on Friday, you don't want to be sitting there thinking, have you actually done this down there? Why did I ask?
That's such a good thing. Got it.
Okay, I can go through a couple of examples in the tutorial seeding. If anyone has something they particularly want me to go over, e.g. with an example, I didn't adopt examples and I got cutting off. And there are examples in the book. When writing the book, there were 2 things I thought were particularly important. One was getting good pictures. So I tapped up all my friends for good astronomical pictures, all the different examples, and my friends were extremely cooperative. So I then started tapping up people I'd never met, and to my pleasure and amazement, they were equally cooperative. So people just liked having their work featured in textbooks. It was very nice. So I was able to write to people So you have this great picture in this article. We got all this technical rubbish on it. Can you just clean it up and send me a simple copy that students could learn on? And normally by return of email, I got something. But the other thing I worked quite hard on was problems, because I think problems are important to make sure you understand. You can. The great analogy is you don't learn to swim by watching the swimming instructor swimming up and down the pool. You have to get in the pool and try it yourself. And that goes for the problems in the book. So we'll do some this evening, just work through them, and I'll give you some to try as well. Yep. So random combination lines occur at very long wavelengths because they're between very high lying stakes. So if you look at, if we go back to working through diagrams, I gave you a little snapshot, but what we're talking about here is forming levels right up here. And then they come down in jumps of maybe 1 or 2 quanta. So I've done it vertical, but it's not. If you start at the F, you go to the D. But you come down in the N levels, you come down 1 or 2 quanta. So they're right at the long wavelengths out there. And because they're so high, the core is a sort of distant memory, and they're not really affected by it. They've just basically, these levels obey the Rydberg formula. The fact there may be sodium instead of carbon or hydrogen doesn't really affect it. The only thing that matters is the reduced mass effect from the core. So everything else goes out, and the radial recombination lines just behave with the Rydberg formula. So N equals 114 to 113. You take 1 upon 114 squared minus 1 upon 113 squared. And that gives you basically the wavelength of the wave number. And you may want to scale the Rydberg constant slightly according to the mass. So you get these small shifts due to the mass. By the time you got to sodium, they're all on top of each other. So you can't tell sodium from potassium, for instance, because they're just on top of each other. But this also applies. So I talked about effective quantum numbers for, quantum defects for effectively 1 electron atoms like sodium and lithium and potassium. Carbon is not a 1 electron atom. I'll go do carbon this afternoon. Very much not a 1 electron atom down the bottom of its scale. But actually, by the time you've got 1 electron out at N equals 100, it's a 1 electron atom. So this formula applies to any atom, no matter what their inner structure is, because when the electron is right out here, it gets very big. Did you discuss the size problem with hydrogen yesterday? The fact that if the size of an atom scales with, I think, n squared. So the orbit that the atom has scales with n. So it scales with n squared. So in principle, you go up to infinity. How big would a hydrogen atom be if it was in level infinity minus 1? I know you can't state that number. Any suggestions? You're allowed to use the size of the universe as your length scale. How big would it be? Small? Medium size? Bigger than this room? Bigger than the solar system? Bigger than the galaxy? Come on, how big's infinity? Yeah. Basically, it's basically if you had n equals infinity size of the universe or b infinity. Yeah. So you don't have to clear it. So what you get in stars is that because there's a pressure, you get an n where it comes off. Because beyond that n, there's too big, it just gets collided while atoms actually gets on. So you get something called the bulb jump, where the bulb in the series stops and goes into. In the sun, it's somewhere n equals 10 or 12. There's that sort of magnitude. After that, you don't get. In the interstellar medium, with these radio recombination lines, they're incredibly diffuse. You can get n equals hundreds. You still can't get n equals thousands. But you get n equals hundreds. And it basically is like it is a measure of pressure almost, because at some point you get collisions that just destroy it. Okay, before I confuse you any further, let's leave it there. And I'll see you is it 2 o'clock we start again? 2:30, right. See you at 2:30.